Hawking's no-boundary proposal. Beyond the dramatic collisions of cosmic brains lies perhaps the most profound reimagining of our origin story. What if the beginning of the universe wasn't just the beginning of space, matter, and energy, but the very birth of time itself? This was the revolutionary concept at the heart of Stephen Hawking's no-boundary proposal. In 1983, Stephen Hawking and mathematician James Hartle introduced a groundbreaking framework that fundamentally challenged our understanding of cosmic origins. Their no-boundary proposal represented a radical departure from conventional thinking about the universe's beginning. Rather than attempting to describe what existed before the Big Bang, Hawking and Hartle suggested a more startling possibility, that the question itself might be fundamentally meaningless. The intellectual leap required to grasp this concept is substantial. We naturally think of time as an eternal flow, a river that has always existed and will continue indefinitely. But Hawking proposed that time, as we understand it, simply did not exist before the Big Bang. This represents a fundamental property of reality itself. To illustrate this counterintuitive idea, Hawking offered an elegant geographical analogy, asking about before. The Big Bang is like asking what lies north of the North Pole. The question contains its own logical impossibility since the concept of north loses meaning at that particular point. There ought to be something very special about the boundary conditions of the universe, Hawking eloquently stated. And what can be more special than the condition that there is no boundary? This profound insight suggests that time itself emerged with the universe, fundamentally transforming how we conceptualize our cosmic origins. The no-boundary proposal offers a specific geometric picture of the universe's origin that differs dramatically from the singularity concept. Rather than emerging from an infinitely small point of infinite density, Hawking and Hartle envisioned the universe with a shape resembling a shuttlecock, smoothly rounded at the bottom and expanding outward. In this model, each moment in the universe's history represents a cross-section of this shuttlecock, with the universe's size increasing as you move upward from the base. Near that rounded bottom, something remarkable happens. The distinction between space and time blurs and ultimately disappears. The three dimensions of space and the one dimension of time become indistinguishable, merging into a four-dimensional space without a separate time component. This smooth geometry elegantly avoids the singularity problem by replacing troublesome infinities with a well-behaved mathematical structure. The mathematical machinery underlying this proposal involves Euclidean path integrals, pioneered by physicist Richard Feynman. This approach represents a quantum system by summing over all possible histories, with each history weighted according to its probability. To make these calculations tractable, Hawking employed Wick's rotation, replacing real time with imaginary time. Think of it like converting a complex problem into a simpler form, similar to how engineers might transform difficult differential equations into algebraic ones to solve circuit problems more easily. This mathematical transformation smooths out the initial singularity. In this framework, asking about what happened before the Big Bang becomes comparable to asking what's south of the South Pole, a category error about the nature of reality. What makes the no-boundary proposal particularly compelling is how it addresses the problem of initial conditions. In standard cosmological models, scientists must input certain starting conditions to explain why the universe has specific properties. The no-boundary approach suggests these conditions emerge naturally from the mathematics, potentially explaining why our universe is remarkably uniform on large scales and has the particular distribution of matter and energy we observe. In this framework, the universe's beginning isn't marked by a chaotic explosion from a point of infinite density, but rather emerges from a pristine quantum state governed by precise mathematical rules. Time is understood as a correlation between the universe's size and its entropy or disorder. As the universe expands and becomes more complex, what we experience as the flow of time emerges. Despite its elegant mathematical formulation, the no-boundary proposal has faced significant challenges. In 2017, Physicists Neil Turok, Job Feldbrug, and Jean-Luc Lehners published a paper suggesting the proposal failed miserably when analyzed using new mathematical techniques. Their analysis focused on a variable called lapse, representing the height of each possible shuttlecock universe in the calculation. When summing over universes with real values of lapse, they found wildly fluctuating, physically nonsensical solutions, not the stable, ordered universe we observe. This technical critique highlights a broader question. Can pure mathematics, without experimental confirmation, truly resolve questions about cosmic origins? The no-boundary proposal currently lacks direct observational evidence, though future measurements of gravitational waves or subtle patterns in the cosmic microwave background might provide indirect tests. The controversy reveals something profound about scientific progress at the boundaries of knowledge. Even the most elegant mathematical models must ultimately confront observational reality. While Hawking's approach offers a conceptually satisfying resolution to the beginning of the universe, the scientific community remains divided about whether it accurately describes physical reality. The implications extend beyond cosmology into philosophy. If time itself began with the universe, then questions about causes before the Big Bang may be fundamentally misconceived. Causality, the relationship between causes and effects, presupposes time. Without time, the very notion of causation breaks down, challenging our deepest intuitions about how reality operates. This doesn't mean the quest to understand cosmic origins is futile. Rather, it suggests we may need to reconceptualize the questions themselves. Instead of asking what triggered the Big Bang, perhaps we should focus on understanding why the universe has the particular quantum state that gives rise to the reality we observe.